Have you ever stopped to think about what a blender, a high-speed train, and some giant factory robot all have in common? Well, they all start with a simple electrical current that they magically transform into powerful, precise motion. It's this kind of everyday magic, really. And today, we're going to pull back the curtain and show you exactly how it all works.
Okay, so here's our game plan. First, we'll get into the fundamental magic that actually creates motion. Then, we're going to learn to speak the language of motors. Speed, torque, and power. After that, we'll uncover a motor's unique personality, check out its energy report card, and finally, figure out how to pick the perfect motor for any job you can imagine.
So how in the world do we get from a quiet little flow of electrons to a roaring machine? Well, it all comes down to this really beautiful interaction between two of the most fundamental forces in nature, electricity and magnetism. And here it is, the secret sauce, the Lorentz force. It all boils down to this incredibly simple but powerful idea. If you run an electric current through a wire and you put that wire inside a magnetic field, the wire physically moves. It gets a push. That one simple push is the fundamental building block of every single electric motor that exists.
And this is where it all began. Way back in 1821, a guy named Michael Faraday showed this off, proving that a wire with current flowing through it would literally spin around a magnet. Now, let's fast forward to the motors we use today. They take that same concept and just run with it. The part that doesn't move, the stator, creates a rotating magnetic field. This field then causes a current to flow in the rotating part, the rotor, which, you guessed it, creates its own magnetic field. And when those two fields interact, the stator's field basically just drags the rotor around for the ride, giving us that continuous, powerful motion we use for everything.
Okay, so now that we know the how, let's talk about the what. As in, what can a motor actually do? And to really get that, we need to learn how to speak its language. And that language really just boils down to three key words: speed, torque, and power.
I want you to think about opening a really, really tight jar lid, okay? That raw twisting force you have to apply with your hand, that is torque. We measure it in Newton meters. Now, how fast you can spin that lid once it's loose, that's speed, which we measure in revolutions per minute, or RPM. It's really important to remember you can have a lot of one without much of the other.
So you've got this twisting force, torque, and you've got spinning speed, RPM. What's the connection? Well, that's where power comes in. Power isn't just about brute strength or pure speed. It's the combination of both. As you can see in the formula, it's literally torque times speed. We measure it in watts or horsepower, and it tells us how fast a motor can actually get work done. So, a motor that can deliver a ton of torque at a really high speed, now that is a seriously powerful motor.
Every motor has its own unique performance profile. It's almost like a personality. And the cool thing is, we can actually see this personality on a graph. It's called the torque speed curve, and it tells us pretty much everything about how a motor is going to act under different conditions.
This graph right here, it's like a motor's EKG. It's a health chart that maps out how much twisting force, how much torque, the motor can produce at every single speed, from a dead stop, 0 RPM, all the way up to its maximum speed. And trust me, understanding this curve is the key to matching a motor to its perfect job. So let's look at the critical moments on this curve. First, you've got locked rotor torque. That's the initial grunt, the oomph it has to get something heavy moving from a standstill. As it speeds up, it might dip down to what's called pull-up torque. Then you have breakdown torque. That's its absolute maximum, its red line. If you push it past that point, it's just going to stall out. And finally, my favorite spot, full load torque. That's the motor's happy place, the sweet spot, where it's designed to run efficiently all day long.
And speaking of that sweet spot, that happy place where a motor runs efficiently, that brings us to its performance grade. Yep, it's time to look at a motor's energy report card, and it's got two main grades we need to check out: efficiency and power factor. All right, first up, efficiency. We use the Greek letter eta for this. It's actually a pretty simple idea. How much of the electrical energy you're paying for is actually getting turned into useful mechanical work. The rest of it, it's just lost as heat thanks to things like resistance in the wires. So think of it this way. A 95% efficient motor turns 95 cents of every dollar of electricity you buy directly into motion. Pretty important, right?
Now here's something that trips a lot of people up. You might think a motor is most efficient when it's just kind of cruising along, barely doing any work. But that's just not true. As you can see here, a motor's peak efficiency, its best possible performance, is usually when it's working pretty hard, right around 75% of its full rated load. So running a big motor with a tiny load is actually super wasteful.
Okay, on to the other grade on our report card: power factor. Now this one's a little trickier, I'll admit. To get it, you have to know that motors actually draw two different kinds of power from the wall. First, there's real power. That's the good stuff that does the actual work of spinning the shaft. But then there's also something called reactive power, and its only job is to build the magnetic fields inside the motor. This is, hands down, my favorite way to explain this. Think about a glass of beer. The beer itself, the liquid gold, that's the real power. That's what actually does the job. The foam on top, that's the reactive power. You need it to have a beer, but it doesn't quench your thirst. And here's the kicker. You have to pay for the whole mug. That's called apparent power, but you only get the real benefit from the beer. So a good power factor means you've got a full pint with just a little bit of foam. A bad one, well, you're paying for a mug that's mostly useless froth.
And I'm not just telling you this for fun. A low power factor, a lot of foam, means you're pulling all this extra current that isn't doing any real work. And that puts a huge strain on the entire electrical grid. It's such a big deal, in fact, that big industrial plants with low power factors often have to pay extra fees and penalties to their utility company.
So, we've covered the science, we've learned the language, and we've graded the report card. Now it's time to put it all together for the most critical step of all, picking the right motor for the right job. It's kind of like casting an actor for a movie. You absolutely have to get the right fit.
And different jobs have totally different personalities. Just look at this table. A conveyor belt needs about the same amount of torque whether it's moving fast or slow. That's a constant torque load. But then look at something like a fan or a pump. As the speed goes up, the torque it needs goes up by the square of the speed. And the power? That goes up by the cube of the speed. It just skyrockets. And then you've got weird ones like a winder, which need tons of torque at low speeds and less torque at high speeds.
And believe me, getting this match right is everything. If your motor is too small, it's going to overheat and fail. Simple as that. But here's the mistake people make all the time. Getting a motor that's too big. That's just as bad. It costs more to buy, and because it's not running in that efficiency sweet spot we talked about, it wastes energy and has a terrible power factor, which costs you more money every single month. The goal is always to find that just right, Goldilocks motor that's going to spend most of its life running right near that 75% peak efficiency point.
You know, from the simplest little toy to the most complicated factory, the electric motor is really the unsung hero that makes our entire world turn. So now we've decoded its secrets, we've learned its language, and we know how to grade its performance. The only question left is, what are you going to do with that knowledge?
Let's study more and like, share and subscribe for such more content and comment something you want to learn.